we're going to discuss periodic properties of elements. This is in the chapter with electron configurations. We're understanding how electrons are filling up the energy levels surrounding the nucleus, and we are going to see that there are regular patterns in properties that are directly related to electron configurations that elements have. So the three periodic properties that we're going to discuss are atomic size, ionization energy, and metallic character. In Chem 2A, this information is found in section 4.8 of the textbook. In Chem 22, it's located in section 9.9 of the text. So again, periodic properties. These are properties of elements which show a repeating pattern, right? So repeating pattern as you move either across a period or down a family. Let's take a look at the first of these periodic properties, and that is atomic size. So when we're discussing atomic size, we're talking about the distance of the valence electrons from the nucleus of the atom, right? How big is the atom? What's the radius of the atom, so to speak? And if you take a look in the Chem 2A text, figure 4.17, in the Chem 22 text, figure 9.33, you're going to see that there is a regular repeating pattern to the size of atoms. And I should state here that we are talking about families 1A through 8A. So these are the representative families. We are not including the transition metals in this discussion, but talking about the representative families 1A through 8A. Looking at figure 417 or 9.33, it's immediately clear that as you go across a period left to right, atomic size decreases. So you can just kind of take that mental picture of that figure and put it in your head, and it's obvious size is getting smaller. The question is, why is that happening? And at first glance, it doesn't seem intuitive that size should get smaller. For example, if you look at lithium in period 2, 3 protons, 3 electrons, some neutrons as well. But by the time you get to the other end of the period that lithium is in, neon, 10 protons, 10 electrons, even more neutrons than lithium. But neon is smaller than lithium is. This seems to be a contradiction. More particles, more subatomic particles, but a smaller size. How can we understand this? Less coming from more, smaller size coming from more particles. Well, here is a way of helping it make sense. As you go across a period left to right, the electrons that are being added are all entering the same valence energy level. So they're not going appreciably farther away from the nucleus. But as you go across a period left to right, you're increasing the number of protons in the nucleus as you move over each block in the period. So this increasing number of protons in the nucleus exerts a greater positive charge on the entire electron cloud and just pulls that entire electron cloud in closer and causes a decrease in the atomic size of elements. That's the only property that you kind of have to puzzle with a little bit to understand. All of the other properties are intuitive and make sense as you think about it. For example, what happens to atomic size as you go down a family top to bottom? Well, if you look at the figure, it's clear that as you go down any family, A-member family, top to bottom, the atomic size is increasing. And that makes sense when you realize that every time you move down a square in a family, you're now adding an additional energy level to the atom, causing its atomic size or atomic radius to get bigger. So that makes sense. We can figure that out. Let's go to the second periodic property, and this is ionization energy. Now, explanation, what are we even talking about when we refer to ionization energy? And use the prefix ion in the term to kind of help you understand what this is referring to. Ionization energy is the energy required to remove one electron from an atom and convert it into a +1 ion. In other words, a +1 cation. So hence the ionization energy, the meaning of ionization in the term, we're taking a neutral atom and converting it into an ion. So here's an example of how we would express this process using chemical equation notation. Here is sodium, a neutral atom, and energy is going to be required to take one electron away from that sodium atom and convert it into a sodium +1 ion. So we are removing an electron, taking it away, and this electron is always going to be a valence electron that we are ionizing. We are removing one electron, taking a neutral sodium atom, and converting it into a +1 ion. Notice that this process would be an endothermic process. Energy would be required to remove the electron and pull it away from the attraction of the nucleus. What patterns do we see in ionization energy as we go across a period left to right? You can check figures and it will show a regular pattern that ionization energy values increase as you move across a period left to right for the representative families. In other words, it's going to take more energy to remove an electron from a neutral neon atom than from a lithium atom, and progressively more energy as you move to over each additional square on the periodic table. In general, you see this pattern of increasing ionization energies. How can we understand that? Why is that happening? Well, if you go back and think about what's happening to atomic size, because atomic size is decreasing as you go across a period left to right, the valence electrons are being pulled closer to the nucleus, experiencing a greater nuclear attraction. Therefore, it's going to be harder to remove a valence electron, and it will require a greater ionization energy value to do that. So across a period left to right, ionization energy values increase. What's happening as we go down a family, top to bottom? Well, we said with respect to atomic size, as you go down a family top to bottom, atomic size is increasing. Atoms are getting bigger. Well, if the atoms are getting larger, their valence electrons would then be farther away from the nucleus. They're going to be less tightly held or experiencing a weaker nuclear attraction, and it will be easier to ionize or remove a valence electron. So as we go down a family top to bottom, we see that ionization energy values decrease, and that makes direct sense. You can figure it out if you stop and think about what's happening in the pattern with atomic size.